We've been looking at the epidemiological toolbox and methods and models and metrics that sort of have a home in the epidemiological toolbox. And now we're going to look at something from the machine learning toolbox. I'm not a big fan of putting labels and stuff. I don't really care if it's from the epidemiological toolbox or the machine learning toolbox or the statistics toolbox and so on. I think we should just use the models and methods that are available to us and the ones that suit our study the best. But it is true that cross-validation, which we're going to look at here, does play an important role in machine learning. And so we usually think of it as a tool from the machine learning toolbox. Quickly just giving you an idea of what machine learning might be. When we say learn, we mean that we give the machine some flexibility in creating a mathematical model of the real world. So when we're not learning, we are designing the model ourselves. So we as humans decide what the model looks like. In machine learning, we give the machine data, so data on the population, a set of instructions, an algorithm, and then allow it the flexibility to create a model for us. And I'm using this big capital M to say our model, our final model that the machine has learned. And the model will look a little bit different depending on the data and our instructions. And there is a lot of research going into different type of algorithms to generate different types of models. Okay, but what do we want to do with our model? Well, once we learn the model, we want to make a prediction. So in machine learning, prediction is an incredibly common task. That's basically what you do. You say, I have a model. I now have an individual. I'm going to put that individual into my model, or not the individual itself, but some data about the individual. And then the machine or the model is going to tell me the probability of not being a case and the probability of being a case. So for individual 1 here, the probability of not being a case is 78% and the probability of being a case is 22%. And this might be in a screening purposes, so it might be, well, I predict that this is going to happen in the future, or it might be for diagnostic purposes, so I predict that this is the case right now. For another individual, these predictions might look different. So for individual number 2, the probability of not being a case was 45% and the probability of being a case was 55%. So there's usually some personalization in these predictions. It's usually not that every single individual gets the same prediction. Okay. So that's machine learning built in two small pieces here, but that's basically what we do. Okay. There's a little bit more to it than that. Okay. But now you want to evaluate your model. So it's one thing learning a model, and then you can make predictions. But are these predictions any good? That's evaluating the model to make sure that the machine is doing something good. Optimally, you would have your model, and then you would gather a new cohort here. And you would make predictions about your cohort at baseline. And then you would wait 5 years to see what actually happens. Let's say this prediction is for screening, so you would wait. And then you would compare the number of cases here, or the different individuals, and if the disease had onset or not, and compare to what you actually predicted. This would be great, but this is unlikely an option in most cases. I mean, you want to finish your PhD at some point. You don't want to just wait around and to check your predictions. Okay. So this is sort of optimal if we could do this all the time, but very unlikely to happen in most cases. So what to do? How do we evaluate our model without having to do this kind of replication? Well, we could use what is called cross-validation. And I'm going to talk about cross-validation and something known as calibration at the same time. But they're two separate things. I'm going to point out what is cross-validation and what is calibration, but just going to bunch them together here in my discussion. Okay. There's a lot going on here, but just follow my cursor and I'll take you through it. Here is the data that I have. Data I've already collected on a cohort. I know whether or not these individuals are cases or not. And I know something about them. Now, up here, I said that you put them into an algorithm and that creates a model. And we're going to do that. But before we do that, I'm going to pull one individual out. I'm going to say, well, this individual, I'm going to keep in a drawer over here. The algorithm is not allowed to see it. It's as if this individual was never part of the study at all. And I'm going to call that individual the testing data. That's a common term, that we have the testing data. And the individuals that are left are the training data. So the training data are put into the algorithm, which then generates a model. Now, once we have the model, I'm going to pick this person out of the drawer again. Let's say, come out here. I'm going to put you into the model, and then I'm going to make a prediction. In this case, the probability of being a case was 22%. So I'm not going to show you the probability of not being a case because it's obviously just 1 minus this, okay? So I picked this person out. I created or learned a model based on the training data, and now I make a prediction about this individual. This individual was never part in the whole learning process. So it's as if I did this, but I had an individual which I held off and didn't include, and that individual now represents an individual from this cohort. This is cross-validation, and then we come to calibration, because we want to have some kind of metric of how well this model is performing, and calibration is one of them. So now I'm gonna read this. I'm gonna say, aha, my model says that there's a 22% probability that this individual is a case. I'm now gonna put you in a bin or a box here, and this box is labeled 21% to 30%. I have other boxes which are labeled 0% to 10%, 11% to 20%, up to 91% to 100%. But because this individual had a predicted probability of 22%, I'm going to put it in this bin here. Now I go back again and I redo this. I put the person, number one person, individual back here, and I pull out another one. I again have my training data, and I again have my testing data. I use the training data to learn a model, and then this individual who was put aside is now put into the model, and a prediction is made. For this individual, the probability of being a case was 5% according to the model. So now I put it in the bin called 0, or maybe not the bin, the box called 0% to 10%. And we continue doing this until each individual has been placed in the testing data. Okay? So you continue this process until each individual has been put in one of the boxes or the bins here. Now, I should note that you don't necessarily have to do this one by one. You could take 10% of your training data if your cohort is big. You could take 10% and pull out and then learn on the rest and then make predictions. That just speeds up the process. But you could also do it one by one. There are trade-offs in both those cases. We won't discuss them here, but that's certainly something you would want to look into if you're going to use this process. What I'm going to do now is I'm going to open the bins and I'm going to look inside them. So we've done the whole process. Every individual in our cohort has ended up in one of the bins, and I'm going to look inside the bin. If I start looking inside this bin here, which is labeled 0 to 10%, so in this bin are people who were predicted to be a case between 0 to 10%. That was their prediction. And then I look at the individuals and see what was actually the case. Well, in this case, there was one individual who did have the disease and 4 that did not. So the actual prevalence was 20%, or prevalence proportion was 20%. But the predictions that our model was making about these was 0 to 10%. So the calibration isn't very good. Because if we had good calibration, we would expect between 0 and 10% of the individuals in here to actually have the disease. But now the prevalence is much higher. So it's a small sample, so we should be fair. In a larger sample, you won't have so few individuals. But this is how we think about calibration. Our model isn't really well calibrated because it's saying one thing, but what we see is another. Go through this to make sure you understand it. It's an incredibly useful tool. Cross-validation is incredibly useful in many cases. Calibration here is useful sometimes, but you could skip this calibration step if you want to and look at, for instance, the positive predictive value or the false negative or the specificity or the sensitivity. Whatever is interesting in your case, you could look at here. And you would get something that is closer to this kind of optimal weighting for a new cohort by doing this.